Okay, all right. So I was going to talk way more about Quaternions. I was planning to talk way more about Quaternions than I ended up doing. So it's actually more about rotations in general, and Quaternions is a part of it. Because I spent way too much time on the previous parts of this talk. Just a heads up, so the last bit is going to go real fast. It's going to be an information dump. So just a heads up. So get ready with your notes or phones to take pictures or something. So I've worked on these things. I'm also short on time on this talk, so I'm not going to stick around and talk about those things, but I worked on those things. And I am working right now on Half-Edge, which is a 3D modeling tool. But today we're going to talk about something else. Today we're going to talk about rotations and Quaternions. And Quaternions is something we use for rotations in games. I'm sure many of you are familiar with it. But when you try to look it up for how they work, you find things like this on Wikipedia. Like, the unit Quaternions give a group structure on the 3-sphere S3, isomorphic to the group spin3 and SU2. In other words, the universal cover group of SO3, the positive and negative basis vectors, form the 8-element Quaternion group. And you're just like, oh, OK, this is not for me. I'm just not going to learn this. It's over. But you know what? Maybe I can find some nice graphics. And then you find some cryptic scribbles. And you're just like, what is going on? Like, what? And you just get tired. And then you're just like, OK, maybe Grant Sanderson can save me of 3 blue, 1 brown. And so you go to his video, and you watch that. And you're like, OK, that was very pretty, but I don't get it. Like, it's a beautiful video. I love this video. But when I watched it, I was like, OK, I sort of get it, but I don't actually get it. And so we're all kind of stuck in this situation with Quaternions. And so we're using them. We have to use them in our games generally, or hopefully, I would say. But it's kind of still this 4-dimensional mystery thing. Like, we just treat it as a black box of just a thing that we interact with, but we don't know of its contents, and we don't want to know of its contents because it's scary and weird, right? And the fundamental difficulty is that Quaternions are difficult to explain. It just is difficult to explain how they work. And that's for a bunch of different reasons. I think most people don't learn about them at school. Like, how many of you learned about Quaternions in school? Raise a hand. OK, that's a tiny amount. That's like 5 people in this entire auditorium? OK. And it's the only abstract algebra that game developers are exposed to, so we're not familiar with that kind of stuff. There's confusing terminology, there's Quaternions, there's rotors, there's versors, and they're deceptively similar to something called angle-axis rotations. But they're not the same thing. They're often portrayed as 4-dimensional objects, which is technically true and fine, but I think it's a little bit of a mistake to do that. And they're also very hard to visualize, and especially intuitively. They also have this weird thing called double cover. And 3D rotations in general are kind of weird. Like, when you look into how they work, 3D rotations are just unintuitive. And finally, you don't have to understand them to use them. I think that's why most people don't know how Quaternions work, because you can just use the black box, right? You find the Quaternion class in Godot or Unity, and you just use that, right? Which is fine. But there are interesting things happening in that box. I'm going to talk about a few of those things. So why do we use them? Like, why do we use Quaternions, like, even though they are this entirely complicated, weird thing? Well, I think that the real question is, how do we use rotations in general? And what choices are we making depending on which rotation representation we're using? And that is going to lead us to why we use Quaternions in the end. And so I think there are quite a few different use cases. One of them is kind of boring and obvious, which is serialization. You want to store the rotations of objects in your data, like in your level. You want to store the rotation of stuff. You use rotations for transformation, which is you have something in one coordinate system, and then you transform that thing using the I don't know which microphone is picking up the speaker. Okay.
Nope. Just too loud. Like this?
Are we good? Testing, 1, 2, testing. OK. So we use rotation to transform points from one coordinate space to another. In other words, rotating vectors, or rotating points. And then we also use rotations for interpolations. And interpolation is just a fancy word for blending. We're blending from one orientation to another. And usually we want that to be smooth, right? And then composition is having rotations combined into a single rotation. And then also for information, because sometimes we store data in rotations that is used for something else. Like for example, like angular velocity is something we sometimes store in rotation data structures. So if we want to figure out, like, OK, how should we store rotation data, these are kind of the points and the metrics we can use to figure out if it's good at the thing that we want it to be good at. So let's start by looking at 2D rotations. I think most of you are probably familiar with the cosine and the sine function. So basically, what the cosine and the sine function does is that it gives you the x-coordinate and the y-coordinate of a vector that is rotated by a given angle. So if you want the vector v, you just shove in the cosine and the sine function, and then you get the coordinates of that vector inside of the unit circle. So it's a length of 1, that vector v. That's kind of the very basics of trigonometry. So angles is probably the go-to thing if we're making a 2D game. We use angles everywhere for the rotation of objects. But if we use the sine and the cosine, we can also get the x and the y-axis of that rotated coordinate space. And so this, and you can do that just by, like I mentioned before, for the x-axis, use the cosine and the sine. For the y-axis, you just swizzle the components, which is you just swap out some components, negate one of them, and then you get the y-axis of that rotated coordinate system. And that's a rotation matrix. OK, I'm very thirsty. I'm sorry. Oh, by the way, at the end, I'm going to link you the slides. So if you want the slides, you can just read them over afterwards. It takes a while to learn these things. I don't expect all of you to just come away from this talk knowing everything there is to know about quaternions. OK, so and these have different characteristics. We can use angles and we can use rotation matrices both to represent rotations, but they have different downsides and upsides to them. And so if we want to use rotation matrices, the strategy is usually, if you want to transform a point, let's say you have a point in local space, so that's P over there. If you then want to transform that point to world space, in case this is a local to world rotation matrix, then you take your rotation matrix, you multiply it by the point as a column matrix or a column vector. So with that multiplication, you then get another vector, and that vector in and of itself is the world space vector. And this is how most transformations work in games. So shaders have matrices absolutely everywhere because the matrices are really good at transformation. They do that very efficiently. And the code for this is very simple. So the first one would be just rotating a point given an angle. And the crucial thing here is that you need to run the cosine and the sine function. And trigonometry is expensive. It takes a lot of computation power to run those functions. So in this case, it's 2 trig functions, 4 multiplications, and 2 additions for the first function. But for the second one, if you already know the rotation matrix, you only have 4 multiplications, 2 additions, and no trig functions. Because basically what you've done is that you pre-computed the results of those trig functions, and then you use those to do the transformation. But it's also worth asking, like, what is the difference between these two? Are there differences that you should be aware of between using them, or are they completely interchangeable? And there's kind of some interesting nuance here, because if you consider the angle of 10 degrees and the angle of 370 degrees, you can kind of ask a very philosophical question of, are these the same rotation? And it's kind of like yes and no. 10 degrees plus 360, like, is that a different orientation or is that the same? But if you use these angles to get a rotation matrix, you get the same rotation matrix. So in a sense, they do represent the same orientation, but depending on the context, you might want to interpret them as, maybe the second one does have a winding. It does have, a thing where it's gone all the way around, and in order to go back to 10, it has to wind back. And so any integer times 360, adding that to 10 gives you the same rotation matrix as just 10. And so, in other words, angles can represent winding, but rotation matrices can't. The way that I usually like to think of this is that the rotation matrices represent an orientation, but an angle represents a rotation. Like a rotation is an action that takes you from no rotation to some other rotation, but an orientation is just a state. Mathematicians will disagree with me, and they will hate me for using these words, but that's how I conceptualize it in my head. So I hope there's no math major in here. Because orientation is a very specific word, but anyway. OK, and then we have interpolation for blending. So let's say you have two angles. You have 20 degrees and you have 130 degrees, and you want to blend between them. Usually, you would use a function called lerp, which is short for linear interpolation. So it just blends between two values based on some percentage. In this case, the percentage is 0.4. So that's 40% of the way from 20 degrees to 130 degrees. So in this case, that gives you 64 degrees. And so that's fine, right? That seems to work well. But then you have a situation like this. So now you have 20 degrees and 310 degrees. So now the question is, what's going to happen if you blend between these two? And now that like philosophical question comes back into play of like, OK, so what does it mean for angles to be similar? Like, do we take the long way around or do we take the short way around? Because I think most people often expect the short way around, but doing a lerp naively here is going to take the long way around because interpolating from 20 to 310, that's going to be 136 if it's 40% of the way. And so there's a lot of weird nuance here. If you want to take the short way around, then you have to be like, OK, so maybe we need to take our first value, add 360 to it, and then we blend them so that it takes the short round. So this is both an upside and a downside with angles, I would say, depending on your use case. So interpolation with angles is ambiguous, but it's also kind of flexible. So if you do want to represent winding, you can. But you can't do that with rotation matrices. Rotation matrices don't have that ability at all. But this is also a very common pitfall. There are many people who fall into this issue of like, oh, it doesn't take the right way around. And then you're trying to use a tan 2 and other trig functions to solve some weird rotation thing. So it can be tricky. OK. So just compare angles and matrices. We can think about the serialization and the storage. The angle is just one number. That's really good. But the 2x2 matrix, you usually store 4 numbers, which is a lot in case you want to store a lot of data. But angles are slow at transforming vectors. You need to run trigonometry to do that, which is slow. Meanwhile, the 2x2 matrix is really good at doing that because there's no trigonometry involved. It's already pre-computed those values. And then when it comes to composition, which is combining orientations, for angles, you just add them together. It's a simple add operation. It's super fast. Interpolation is also just a lerp, which is also super fast. And you can represent winding with it. Meanwhile, the 2x2 matrix, composition is OK. It's quite a lot more multiplications there, but it's possible. But interpolation, that's when you're going to need trigonometry again. And there's no way to represent winding with 2x2 matrices. OK. Now, there's one more way we can represent angles in 2D that nobody does in game development. And they probably shouldn't, but we're going to talk about it today. And it's one of those things where mathematicians are sometimes bored. And they come up with a weird concept. And they're like, wow, wouldn't this be wacky if we just had this thing? And one of those wacky things is the concept of I. So in math, there's something called the imaginary unit. And so that is this letter I. It's a variable. And the only thing we know about it is that if you square it, in other words, you multiply it by itself, you get -1. There's no number. There's no real number that has this behavior. Like 1 times 1, that's 1. -1 times 1 is also 1. So none of those give you -1. There's no number that gives you -1 if you square it. But we can just invent it. We can just say, OK, what if we had a thing where if you multiply it by itself, we get -1? This is a really weird idea that has massive consequences in physics especially, but also in mathematics. It's a really, really beautiful concept because it's so simple, but it has so many things that happen as a result of that. So if you want to read about it on Wikipedia, I've spent many hours doing that because it's just fun and interesting. I don't know if you're that type, but anyway, so we can do math with this, right? This is just an algebraic formula. If we square it, we get -1. So we can write some equation like 2i times 3 minus 2i, or yeah. And then maybe we can simplify that. So we get 6i minus 4i squared. And here's where we can use our axiom, right? That the axiom at the top is that if we square it, we get -1. So the second term, -4i squared, becomes 4, because I squared is -1, right? It's just like multiplying by -1. OK, so that's sure, fine. It did that. That might not be very interesting, but we can try some more. So how about I cubed? So that's I times I squared. And I squared is -1, so I cubed is -I. OK, we can do another one. So we can do this one, multiply by I on both sides, and then we can separate it like this. And we can see that we have some kind of behavior where quite often it tends to simplify down to a very specific structure. And that structure is that we have some coefficient of I plus some coefficient that's just a real number. So you can see that all of these have that property. The one with -I just has 0 on the real part of that. And these are called complex numbers. And that's, again, when you have some coefficient of I and a real number. That's a complex number. You can kind of separate it into two components. So if we have a complex number A, there's a real part plus an imaginary part times I. OK. So we can kind of generalize this. So if we have two of them, two complex numbers of arbitrary values, so those AR, AC can just be whatever number we want. And then we can see, OK, so what happens if we multiply two arbitrary complex numbers together? Then you can see that we get this if we just expand the equations. And then once again, we're met with this thing where we have I times I, which is I squared, and I squared is -1. So that term becomes negative, and both of those i's disappear. And so simplifying it again, you can see that that hops on over there to just be a real number. And this in and of itself is also a complex number. Like we could just keep on doing this, and at the end, we get another complex number. So it's got a real part, and it's got an imaginary part. I did not turn off audio on my phone. I apologize. There we go. OK. So, and we can just implement this in code. There's nothing stopping us from doing that. Because I remember when I was reading about this, when I was learning about this, I was like, OK, but how do you represent I in code? Turns out you don't actually do that. You don't have I in your code. The only purpose of the imaginary unit is to inform you how we would write equations using this and how the algebra would unfold. So if you want to write a C# class that uses that's a complex number, you would write the multiplication operation like this. You would just have the same calculations as you have here. And then the imaginary part is just one of the float variables in this type. OK, so one thing that's kind of interesting about complex numbers is that they are pretty similar to vectors. So if you have a 2D vector, a 2D vector in code, it would have two components. You have two numbers, a and b, right, or x and y. And these two numbers kind of implicitly refer to the coordinate axes of your space. So the x-axis and the y-axis of your space. And so it's kind of implicit that vectors in games have this x and y connection. That's, if you just think of it as two numbers, it doesn't really have that connection. But it's important to remember that this is a spatial concept. It's related to the coordinate space. And so a different way of writing vectors that's a little bit more mathematical is to write a times the basis vector x plus b times the basis vector y. So this is called a rectangular form of writing it. And the nice thing about writing it like this is that it's easier to do algebra with it, because now you just have something times something plus another thing times another thing. And so then if we represent vectors, we can write them as 2x plus 1y instead of just 2 and 1, which we usually do in code. And the same goes for complex numbers, except in this case, complex numbers don't have a basis of x and y. They have a basis of 1 and I, the imaginary unit. So we have some quantity of a real number, which is just multiplying by 1. So that's just a number, right? And then you have some quantity multiplied by the imaginary unit, which is the imaginary part. And so we can set up a coordinate system for this as well. So this is called a complex plane. So on the horizontal axis, we have the number line, the usual number line of just real numbers we're used to using. But then on the vertical axis, we have the amount of the imaginary unit. And here too, we can have vectors. We can place vectors in this space and geometrically visualize them and see how they behave and function. And so this part in particular is what we're interested in now, because we can do algebra with this, and because we can visualize them as vectors, there's a really neat consequence of this that's going to happen. I promise this is related to rotations. I'm deep into this now, and I apologize if this is boring, but I'm getting there. OK, so I can talk at length about this. In fact, I have. So if you want to learn more about this particular part, I have a talk about that. It's on YouTube. So if you want to learn about multiplying vectors and geometric algebra, you can feel free to go there. Anyway, so now we have a coordinate system. So in this coordinate system, we can visualize our complex numbers. So let's say we have a complex number of a equals 2 plus I, and then another one, b, which is -1 plus 2i. So we just have some complex numbers here. So now the question is, what happens when we multiply these two together? Because 2D vectors, you can't multiply 2D vectors, but you can multiply complex numbers. So what's going to happen? Well, we get this vector right here. And so this might not look very remarkable at first, but if you analyze this and kind of break it down, what's happening here is actually kind of weird. So what's happening is that if you consider the angle of the complex number a, and the angle of complex number b, the angle of c is both of those angles added together. And so just from this simple rule of having I squared equals -1, we suddenly have a mathematical construct that combines angles, which doesn't seem like it was supposed to be doing to begin with, right? I think that's kind of weird and interesting. And what's more is that the length of this vector is actually the length of A times the length of B. And so then we get the length of C. So not only does it add up the angles, but it also multiplies the magnitudes of A and B together. So if that is the case, that the lengths multiply together, you might ask yourself, what happens if one of these complex numbers is normalized? If it's a unit complex number, it has a length of 1. Well, if you multiply the lengths together, then that means that the length of the resulting vector is going to be the same as b, because a is just 1 in its magnitude. And so the angle of a is directly added to the angle of b, and then we get the result c. And so this is how complex numbers are kind of like magically related to rotations in that sense of you can just multiply a complex number. You can take a vector, represent it as a complex number, multiply it by a complex number, and then you will have rotated the vector by the same rotation as that complex number. And what's more, you might be able to see that if A, in this case, was pointing directly upwards, that would be a 90-degree rotation. And so in a sense, multiplying by I is a 90-degree rotation. This is a really, really fundamental thing in math, and it's a really cool property. I would have loved to have time to talk about this formula. This is one of the most beautiful formulas in math, I think, because you can just invent this concept of I squared is -1, and all of a sudden this makes a connection to radioactivity and springs and quantum physics. It's everywhere in physics. It's really, really cool. Anyway, so we kind of have 3 different ways of representing angles in 2D. We have just using an angle, straight up. We have a 2x2 matrix, and we can use a complex number. And in a sense, the complex number has the same values as the x-axis of the 2x2 matrix. It's just the same numbers. It's just that we have a different interpretation of it that makes it a little bit different. So we can add complex numbers to our little table here to compare them to see which one works best for our situation. But nobody does this. I don't think anyone uses complex numbers for 2D rotations. I think even if you do, you probably just store oh, here's the x-axis of the 2x2 matrix, and then you compute the y-axis when you run it, right? OK, so nobody does that. But that's OK. I'm talking about it for a reason. OK, so now we're moving on to the 3D rotations. So 3D rotations are a lot more complicated. In 2D, there's only one plane of rotations. All the rotations take place in the same plane. But in 3D, there's an infinite number of planes of rotation. You can pick any plane that's oriented in any way and then rotate in that plane or around some arbitrary axis, right? Another thing is that in 2D, there's not a whole lot of ambiguity. So in 2D, there's generally only two different coordinate systems. Pretty much everybody agrees that x should be pointing to the right, and y is then either up or down. It depends on the coordinate system and the context you're in. So if you're making a website, you're doing HTML or CSS, then y is pointing downwards because 0 is at the top, and then you scroll down to read the rest of the page. But then many games have y up for other reasons. So you usually see these two different ones. So the one on the right is usually for UI, because we're kind of used to doing it that way. But in 3D, there's more ambiguity. So I made this chart a while ago just to try to get a sense of what is the consistency here, what do we all use in all of our different applications. And so in 3D, there's a concept of handedness, because in 3D, there's two different ways to orient space. And they're mirror images of each other. So you can kind of use your hands like this if you make these gang signs. So if you imagine your thumb is the x-axis, your index finger is the y-axis, and your middle finger is the z-axis. These are mirror images of each other, right? You can't align them with each other. It's impossible. They are different. And so every 3D application uses one of these two. And it's very rare that they let you switch between these. I don't think I know any that lets you switch handedness. But I want to change that. More on that at some other point. I don't know. Anyway, so usually they can be either left-handed, right-handed, and they can either be y up or z up. So that's just picking which axis we want to be the up axis. And you can see that it's kind of spread out. Everybody is disagreeing, except everybody's agreeing that Unreal is wrong. I think that's the only thing here. And Tim Sweeney did actually apologize to me on Twitter for making that decision when he was very young. So mistakes were made, and Unreal is just like that now. OK. But there's some good news, good news between 2D and 3D. So the matrix form is actually pretty much exactly the same in 3D. Yeah, the 2x2 matrix just readily expands to a 3x3 matrix. And just like the 2x2 matrix, you just directly store the three vectors of your coordinate space. So the columns of the matrix are those three vectors of that coordinate space. So 3x3 matrix, we could just toss that in there. We have that one already. Transformation is once again fast, but there's a lot of numbers now that we need to store. 9 is a lot of numbers. And interpolation especially is really bad for 3x3 matrices. There's a lot of trigonometry you have to do there to blend between different orientations using those. Now, before we move on, I want to drill this into your head. It's always this order. Everybody agrees on this, and if somebody disagrees on this, they're just objectively wrong. XYZ is always in the colors RGB. If you see a green arrow in a 3D applications, that's the y-axis. If it's blue, it's the z-axis. If something is called X, it's going to be red. It's always those, which I'm very grateful for, that there's not a whole mess out there of disagreement on this. But then, of course, there's the handedness. There's disagreement about which order we should consider the fingers. I always stick to thumb, index finger, middle finger. That way, you're not going to have any issues or run into ambiguities. And then finally, with these two handedness, you have a right-handed coordinate space and a left-handed coordinate space. There's another thing that you might not be entirely aware of, which is that rotations are also determined by the handedness of the space. So if you make a thumbs up with your hand, if you consider the thumb to be the axis of rotation, the curl of your finger, the direction your fingers are curling in, that is a positive rotation. So if you increase an angle, it's going to rotate in that direction. But again, it depends on handedness, so you need to know if your application is left-handed or right-handed. So if you're using Unity or Unreal, it's left-handed, so then you use your left hand to make all of these gang signs and gestures. If you're using Blender or Godot, it's going to be right-handed. Most things are right-handed. In math, it's pretty much always right-handed as well. So right-handed is kind of the standard in general. So it's just kind of weird that both Unity and Unreal are left-handed. It's kind of an anomaly, but it's also very common in the games industry. OK, and then another one is also useful to think of x, y, and z as a cycle and not as a linear graph in 3D. That cycle is useful. More on that later. OK, I need water. My mouth is dry. I'm going to try to make room for questions at the end. OK, so let's see. If you then consider this whole thing of an axis and then an angle around that axis, just rotating around the axis that is our thumb, that is actually one of the ways that we represent rotations in 3D. And it's actually called the axis angle. Yeah, it's just called axis angle, sometimes angle axis. And so the idea is that we have a normalized vector for the axis, and then we have an angle associated with that for how much we want to rotate around that angle. But there is an even cooler way to represent this, which is instead of having an axis and an angle, you just multiply the angle by the axis. So the length of the axis determines how much you want to rotate. And so this is kind of like a demonstration of how that works. So the vector in the middle is the rotation vector. And as it grows longer, you rotate the coordinate system more. And you can pick an arbitrary axis for this. Like whatever axis you pick, you're going to be able to rotate in that axis. So it doesn't have to be aligned with x, y, and z. So this is called a rotation vector. If the angle is stored separately, it's usually called axis angle or angle axis. But I like the rotation vector better because it doesn't have redundancy, and it's only 3 numbers instead of 4. So that's a really, really useful way of doing it. This is probably my favorite rotation representation because it's very intuitive. Like, I don't know about y'all, but this is I can see how this works. It makes sense in my mind that this is how it rotates objects, unlike some other rotations. OK, so this is a rotation vector. I love it, but it's not very good at transforming. It's also not very good at composing, like adding multiple rotations together. It's OK at interpolating. I think it was a hard time. I had a hard time finding good resources on this, and I didn't want to spend the time calculating it. I think it's pretty slow there too. But the thing that's cool about rotation vectors is that they do allow you to have winding. The thing where you rotate something beyond 360 degrees. So rotation vectors are actually used quite a lot for angular velocity. Specifically, because you want to be able to say that something is spinning faster than 360 degrees per second or radians per second or whatever. OK, so another thing that's useful to keep in mind is that sometimes it's good to think about rotations as happening in a plane rather than around an axis. Because in 2D, there is no z-axis. But we quite often kind of assume there is one or like imply that there's a z-axis, but there isn't really. So one way to think about what direction is a positive rotation is that x always goes towards y. And that's where the cycle of x, y, z is really, really useful to keep in mind. So a positive rotation is always x rotating towards y. I much prefer this way of thinking about it rather than counterclockwise and clockwise. I hate those words. They don't work in 3D. I don't know if people are aware of that, but I've seen people talk about, oh, rotations are clockwise. And I'm like, that's ambiguous. I'm the only one with this problem, it seems like. But anyway, so in 2D, there's only one plane, and that is the xy plane. That's what makes rotation a little bit easier in 2D. And also, it's good to remember that positive rotations then goes from x to y in the xy plane, regardless of whether or not it's y up or y down. But in 3D, it's a little bit more complicated because now there's not just one basis plane in our coordinate system, but we actually have 3 basis planes. And these basis planes should be called xy, yz, and zx. Some authors like to call zx xz. Do not do that. You're going to make life hell for yourself. Don't do that. It's zx. Remember the cycle. Remember the cycle. OK, so if we have these 3 basis planes with positions, we have the 3 basis vectors to represent positions. So maybe we can represent rotations by composing 3 different rotations in each of these planes, right? So then the question is, can we do that? Can we construct that type of rotation? And all of you know about this. And all of you know that this is possible because this is Euler Angles. This is just, OK, so what if we take some rotation around each axis and we're going to, whatever ends up as the result of those 3 actions is going to be the final orientation of our object. But there's a problem here. And the way to fix that is to first look at a cat. So here's a cat. Credit to End Vertex, by the way, who provided me with this cat model. So let's say we want to rotate this cat. Highly recommended, by the way, rotating cats. So let's say we want to rotate it negative 90 degrees around y, and then negative 90 degrees around z. And this is a left-handed coordinate system, so you can use your left hand to be like, oh, which is it going to rotate around? So if it's negative around the y-axis, you can use your left hand to figure out beforehand which direction it's going to go. OK, so let's just do that rotation. So negative 90 around y, and then negative 90 around z. And now the cat is pointing directly upwards. And so now there is a pretty big problem with Euler angles, or actually with 3D rotations in general, because if you reverse it, you do z first, and then you do y, you get a different orientation. So the cat on the right is rotating on z first, and then on y, and they end up at different rotations. And so, this is a creaky floorboard. Sorry. And so this concept is called non-commutativity. So it basically just means that the order in which you apply rotations matter. So if you change the order of the rotations, the end result is going to be different, which is different from the way that regular multiplication works. Like if you multiply two numbers together, you can generally swap them and you get the same result. But that's not the case for rotations as a concept. And so then the question becomes, OK, so if the order matters, and we have this thing where we want to represent a rotation by rotating around each of these axes, what order should we apply these in? And so I would go to this. Again, we have the cycle. We have x, y, z. We should just follow x, y, z, because that's the way we do everything. And usually, the math kind of works out better if we do it that way. But then a more sinister question is, what order are we actually applying them in software today? And so let us all consider Unity, Godot, Blender, and Unreal. So first, let's just look at Unity and experiment with the rotations there. So we're going to have a transform, and then we're going to rotate it on the x-axis. And it's like, OK, cool. That's rotating around x. Then we do y. And it's like, oh, OK, so that's world space y, and then local space z, like its own z-axis, I guess, right? OK. Then maybe you, yeah, so it kind of seems like it's like x, and then world space y, and then local space z, which is kind of weird, right? And for the first rotation, it doesn't really matter if it's world or local, because they align, right? OK, so then you might play with it some more, and you're like, OK, so if we do y, and then x, they're both local space, and then z is now also local space. It's like, oh, OK, so now they're all just local. But if we do z, and then after z, sorry, it's not live. There we go, x, and then we rotate around x. Now it's around world space x, right? And that's world space y. This is confusing. I think a lot of people have issues with Euler angles precisely because of this reason, where as soon as you have a rotation on more than one axis, things get confusing with Euler angles. And so you kind of have, yeah, it's in world space there. But if we just think of the rotating around its own axes, we ignore the world space thing, we can say that Unity does y, x, z as the order of the Euler angles. OK, so what about Godot? So we can go to Godot. We have the rotation there, and helpfully, Godot actually tells us the rotation order directly. Godot is like, hey, by the way, we're y, x, z in this household. It's like, oh, OK, cool. And so it just says y, x, z, and that is the same as Unity. This is good news, because they agree on something. And so we can test it out here. It's y, it's the local space y-axis, and then x, it's a local space y-axis. And then finally on z, that's the local space z-axis. Cool, so that's exactly the same. So that's great, good news. But then the bad news is that if you look a little carefully, there's a drop down here. And so we kind of run into this situation, which is like, both good and bad news, right? Like, we have the flexibility to do this, but also, oh no, this is not standardized. Like, we have to be able to make a decision about this now, and we're forced to, right? But I think most people just stick to the default setting in general. But so it's more so that Godot has that by default. It's not forced on you, but that's a default setting. Now, what about Blender? Well, Blender also tells you what it does, and Blender is XYZ, which is not the same order as the other two. And then we're like, OK, all right, so OK, we got the x-axis there, and then the y-axis, but that's the world space y now, but it said XYZ, so OK, is that not the local space one? And then you're doing the z-axis, and it's also just wonky, and then we're like, OK, fuck it, I'll just switch to yxz, because that's what Unity and Godot are using, yxz. Let's just use that. OK, so we do y, hell yeah, now it's working, and now we're doing the x, and now it's wonky again, because now it's world space for some reason instead of local space, and everything is just wonky and messy. So my students made a shirt at one point with quotes. It's quotes from their teachers. And the quote that they picked from me was, at some point in some lecture, I said that nothing is consistent and everything is garbage. I don't remember the context for that, but it applies here. And so this is just a mess. It's really annoying to find consistent information about this, so you kind of have to experiment your way there. But there's a really, really cool thing that's a bit of a saving grace here. So now we're rotating some cats again. If you consider the local space rotations of the left cat, you can see that it rotates around x, and then around y, and then around z. And then look at the cat on the right side. We're doing world space rotations instead. So world space z, world space y, world space x. These two end up with the same rotation, which is kind of counterintuitive. Like, I wouldn't expect that to be the case, but they end up with the same rotation if you reverse the order and switch whether or not you're using local or world space rotations. The more accurate terms for this is intrinsic and extrinsic. So intrinsic is its own rotation space. Extrinsic is the parent space, so the world space rotations. And so yeah, it's kind of cool that they actually line up that way. That way, we don't duplicate our standards to have even more standards, right? And so this rotation order and intrinsic axes are the same as the extrinsic axes if you swap the order of those. And getting familiar with the concept of extrinsic versus intrinsic rotations has saved me a ton of time of swapping quaternions, inverting one of them, and you add a third quaternion, and like subtracting quaternions. I don't know, like swapping rotations until it works, right? I don't like doing that. And after learning about this, I've saved so much time. But the problem is, of course, that it's kind of annoying that Godot says yxz, and Blender also says yxz, but they don't tell you if it's intrinsic or extrinsic. And that kind of matters if you're a nerd like me, right? So if you want them to line up, it's kind of annoying that it's like that. So if any of you are contributing to either of these two, it would be super cool if you clarify that so that it's visible in some way. You don't have to use this syntax, but this is what I saw on Wikipedia. I think it's a pretty good syntax, but whatever. Anyway. OK, no, my mouth is very dry. I'm sorry. I need to drink again. OK. Oh, can I have some more water, by the way? I'm almost out. Oh, thank you. OK, so now we're showing this with the intrinsic rotation order. So this is the local space order. All right, so Blender in intrinsic order is zyx. Which means that in extrinsic, it's xyz. And then Unreal is actually in agreement with Blender here. Unreal and Blender has the same rotation order. But of course, they agree on that, but they don't agree, because Unity is left-handed y up, and Godot is a right-handed y up, and Blender is right-handed z up, and then Unreal is left-handed z up. Like, they're all different. Like, none of them agree there. Anyway. But there's one more wrinkle with Euler Angles that I think most of you have probably heard of. I don't know why people know about this concept so clearly and why people talk about it so much, but it is kind of interesting. And that is if you set the rotation of x to 90 degrees, And then you try to rotate the other two. We rotate y there. OK, so that's around world space y. And then z is the local space z. We have lost a degree of freedom here, right? If we set x to 90 degrees, the z-axis is never going to rotate out of that plane. Both y and z control the same rotation now, which kind of sucks, because you're like, what the heck? I just want to rotate it up, like get up, you know, and it doesn't work. So this is known as Gimbal Lock. So Gimbal Lock is a problem with Euler angles only. No other rotation representations have this issue. Because I think a lot of people have this misconception that Quaternions solve Gimbal Lock. It's more so just that Euler angles have Gimbal Lock issues. None of the other ones have issues with that. OK, well, so you know, Gimbal Lock in games, I haven't found it like that big of an issue in practice. But let's say you're hurtling toward the moon at 6,000 kilometers an hour in 1972. And you are an astronaut, and you have to make the call to talk to Houston and say, OK, I'm not sure what just happened. All of a sudden, I saw a warning light, and I got a no attitude and a gimbal lock. That was Thomas K. Mattingly II on the Apollo 16. So they were doing the moon landings. So on the spaceship, there is a physical device that's the IRL Euler angles. And that's a gimbal. It's got this gyroscope thing inside of it, and that keeps track of the orientation of the spacecraft. So it's a very literal, actual Euler angle in physical space, right? And literal space. And this gimbal, this little ball that shows you the orientation of the spacecraft, literally has a red region at the top. That red region tells you, don't go there, because that's gimbal lock. You're going to lock up your axes, and you're going to lose a degree of freedom if your spacecraft is oriented so that it hits those. And that happened on the way to the moon. And so basically what you have to do in the spaceship is that you have to manually realign the spaceship and the coordinate systems, like manually using the stars in the background to like make sure that you got it right. I would be terrified of doing that. But anyway, they made it out fine, and nothing bad happened. But yeah, I just thought it was an interesting tidbit. But OK, so another problem with Euler angles is that they are, first, it's messy. So if you want to convert Euler angles to a 3x3 matrix, you're just like, OK, right, there's a gazillion different standards. And actually, the Euler angles we use in games are actually called Tate-Bryan angles, which nobody calls them that, but that's what they actually are. So you need to be like, OK, which one of these is mine? So that's when you need to figure out the orientation order of your game engine. And then you're like, OK, so I finally found it. There it is. And this is 6 trig functions and a bunch of multiplications just to convert from Euler angles to a 3x3 matrix. So Euler angles are generally kind of bad at everything. They're just not good at most things. They are just 3 numbers, though. That's nice. And they can represent winding. You can wind them an infinite number of times. Problems, though, is, of course, gimbal lock and all the other things I mentioned. OK, I need some more water. Oh, shit, I'm not doing well on time. We're going to speed run the Quaternion section. I hope you're ready. OK, probably not going to have that much time for questions. Feel free to just ask me whatever. I'm going to stick around for the whole event. I'm going to be joining the game jam. Don't be afraid of annoying me or disturbing me with a question, because I'm not annoyed by that. People always message me afterwards, and they were like, I wanted to talk to you, but I didn't dare to talk to you or whatever. Don't be that person. Just it's OK to talk to me. It's fine. I appreciate it. OK, so Quaternions. It's time. We've talked about literally everything except Quaternions in this talk titled Quaternions. And so we had this thing for 2D rotations, where we made up this thing called the imaginary unit, where if you square that, we get -1. So if we want to expand this to 3D, it kind of makes sense to be like, OK, so in 2D, we had only 1 plane of rotation. But in 3D, we have 3 planes of rotation in the axes, like the basis planes of that coordinate system. So let's just add 2 more. They behave the same way. If we square them, we get -1. They behave exactly the same way, but they are distinct. They are not the same. So I is not the same as j, but if you square any of them, you get -1. So it's actually a little bit more accurate to say that in 2D, for our complex numbers, we should be using k here instead of I. So because k represents the xy plane of the 2D coordinate system. That's what k represents. And in 3D, we now have I, j, k, the three of which are referring to the basis planes of that coordinate system. And we also still have a real number, of course. So a complex number has a real number and a single imaginary unit. But the Quaternions have a real number and three different imaginary components. Now, in order for this to work out mathematically and algebraically, we need another rule. So we need to just add one more thing, and that is that I times j equals k. Usually, it's not written this way, though. If you look this up online and on Wikipedia, you're generally going to see it written this way instead. So this is the definition for Quaternions. All this says is that I squared is -1, and j squared is -1, and k squared is -1, and I times j times k is also -1. This creates a complete algebraic structure. So you can do math with things that have all of these behaviors, and you're going to have the algebraic behavior of Quaternions. Now, it might be difficult to memorize, like what happens when you multiply all of these components together. Like this directly follows from the definition at the top. You can work out what happens when you do all of these pairings of I and j and k. And so this thing of like multiplying I by j and then we get k, that is what these things are trying to tell you. Like that's what all of these are about. So like, oh, this blue circle is like when you multiply by k, you permute the result of that around that circle. I think that's a really confusing way to explain that. So instead of just having a table like this or just having these cryptic images, the way that I usually like to think of it is just think of them as a cycle like this. So if you just start on one of these, so I, and then times j, you go to the next one, then you get the third one. So I times j is k, k times I is j, just go around that circle. I think that's pretty easy to remember. And then if you go the opposite direction, the result is also opposite. So if you go the opposite direction around the circle, if you do I times k, so that's going the opposite direction, you get -j. So opposite direction, negative sign, positive direction, positive sign, that's it. I think that's a much nicer way to do it than whatever this is. OK, so a Quaternion is then an algebraic object that has some amount of I, some amount of j, some amount of k, and a real number w, which is also just some number, right? So in Unity, when you create a Quaternion, for example, you specify the values x, y, z, and w. So that's what these coefficients are here. Now, there's one more thing to know about Quaternions, is that Quaternions are kind of a general concept. You can use Quaternions for a bunch of different things, not just rotations. So for rotation Quaternions in particular, they have to have a length of 1. So that's required for unit Quaternions used for rotations. And that's the same thing we had for the complex numbers, right? Like we had to normalize the complex number to make sure that the length of the result remained the same. OK, so then you might have the question of like, how do we rotate this thing then? Like what the heck does all of this have to do with rotations? Like, yeah, I get that it's kind of similar to the other ones, but so here's probably the most important slide if you want to try to remember Quaternions and how they work. Let's say you have a normalized axis, and you have an angle that you want to rotate around that axis, in radians in particular. If you want to construct a Quaternion that represents that rotation, then all you have to do is this. So you take the cosine of half of the angle, more on the half later, and then you take the axis and multiply it by the sine of a half of the angle, and then that's going to be the coefficients for your I, j, and k. So that's how you get a Quaternion that does that rotation as the axis angle form. And so the cool thing about this is that we have pre-computed the trigonometry, just like rotation matrices pre-compute the rotation by not having to do the trigonometry live. And then also this part, it kind of stores the plane and the axis of rotation, but it is scaled by sine of half of the angle. So it's not quite, you can see that it's similar to axis angle, but it's not really the same thing because, again, we pre-computed the results of trigonometry on that angle instead of storing the angle directly. And so this algebraic structure here for Quaternions this is what makes quaternions really, really powerful, is because we have pre-computed all of this stuff, and that makes it so that the composition of combining two rotations, all we have to do is multiply them together. If we have a quaternion A and a quaternion B, just multiply them, and it's as if we've taken two rotations that happen one after another. Whatever axes we're rotating in, however we rotate them, that's going to be composition. There's kind of two different interpretations of A times B. So either we're rotating, you can interpret it as rotating A around its own axes by B, or you can interpret it as we're rotating B around its parent space, or in world space, by A. These are equivalent, so you can kind of interpret it either way. And remember that if you swap quaternions, you get a different result. So you can't just swap however you want. And the whole reason we're using quaternions is because this is computationally more efficient than matrices. That's why we use quaternions. And then finally, transformation is also kind of weird. So with transformation, you take your quaternion A, you multiply it by your vector, typecast to a quaternion, and then you multiply that by the inverse of the quaternion. And that's how you take a coordinate and transform it using a quaternion. In other words, rotating a point. And the reason we use half of the angle is because the transformation applies the rotation twice. And so half of the angle is required so that it doesn't overshoot. This is also why quaternions have a winding of 2. It has double cover. Every rotation is covered twice. So a rotation q is the same as negative q, which is kind of weird because it makes it both useless for angular velocity, but it's also annoying that you sometimes can have quaternions that look different, like algebraically or in terms of its coefficients, but they are the same orientation. And just like complex numbers, you can just write the code for this if you just follow the rules of the math. I've laid out everything you need to know to write a quaternion class. You just have to do all of that math, or just copy it from Stack Overflow, I guess. Either is fine. OK, so then you might ask, which one should you use? Well, that kind of depends on your use case. And the answer that most game engines have is that we're going to use all of them, because all of them are useful in different use cases. But the real power of quaternions is that composition and interpolation is really, really good in 3D. Quaternions are just performant. They are much faster computationally. The downside is, of course, that they're confusing. They're just really confusing. But they're fast. But yeah, so which one should you use kind of depends. But if I were to summarize this in apparently 2 minutes. So Euler Angles, they are useful. Well, we have Euler Angles, matrices, angle axis or rotation vectors, and quaternions. I don't know. So I would say that Euler Angles are horrible in almost every single way, but they're easy to read. It's good for user input. It's the thing you put in a UI so that you can rotate 90 degrees around x. It's easy to do that thing with Euler Angles. But otherwise, they're horrible for every reason. Matrices are super fast for transformation. That's why they're used everywhere in shader code, in every single vertex shader out there. Angle axis is pretty much only used for angular velocity. I don't know if people use them for pretty much anything but angular velocity. And then finally, quaternions they're just really good at composition and interpolation. They're useful for most rotations in gameplay code. OK, and then if you then want to get started with quaternions today, here's a simple guide. So I would have loved to have more time to talk about all of this, but I didn't plan well, honestly. And so if take a picture of this if you want a summary, and you can just study this, and then you're going to be a 4-dimensional god. But I'm also going to link the slides at the end, unless I get kicked out. So thank you so much for coming.